like I said, Euler's method is an extension of something you already know, linear approximations. So what you already know is something like approximate f at 2 if f of x equals s squared with the equation of a tangent line. It's probably not how it's exactly worded, but linear approximations, right? Calculate the tangent line equation, plug 2 into it. Correct? So what's the equation of the tangent line here? Point's 1, 1, right? And the slope would be 2, right? So if we're going to use this to approximate f at 2, we plug 2 in for x, right? So we'll put approximate. Or what do we get? Yep. Okay. Euler's method is something similar to that. A little bit more involved, but not much. Okay. Is the approximation above or below f at 2?
Would it be below because concavity is up?
Below because f is concave up. Correct, right? So you have your parabola, your approximation is going to be out there. So this would be 2 on the x-axis, right? All that still applies. All right, so you good with that? Okay, so the difference with Euler's method, so here we're given the original function. We could be given a derivative with this as well at a point, right? With the Euler's method, usually you'll be given a differential, something like that. That's why we usually pair it with slope fields, because it's all differentials work. Okay. So we're also we need an initial condition. So we'll give you an initial condition. The question might say use Euler's method to estimate y at 2 using the change in the x value 0.5, and I'll explain what that is. They might also say using 4 steps. Again, I'll tell you what that is. Okay. So in this specific situation, I don't even know what that curve looks like. And we'll just give it a nice little round shape. we are starting at 0, correct? So x equals 0, we start here. And what we did on the last slide was we would approximate using a linear equation, correct? Well, Euler's method is linear, but it recalculates the slope in this case, every 0.5 units. Right, so we're going to have a tangent line here, but at 0.5, we're going to recalculate the slope, and we're going to have a new one. And at 1, because that's another 0.5 units, correct? We're going to have another one.
So Euler's method is the same thing as an
It's a linear approximation. You're just recalculating to follow the curve more closely, right? At 1.5, we're going to recalculate, right? And then at 2, we're going to have an approximation that's closer than linear approximations, but still not exact most of the time, right? Okay, so basically it's the same thing. You're just recalculating the slope 4 times. And so 0.5 could be the step size, or you can say using 4 steps from 0 to 2, 1, 2, 3, 4, right? Let's see both. Okay. So, how do we do that? And your book sucks at this, that's why I don't use it. Okay, so the best way to do it is just to set up a table where we start with our xy, our initial condition, 0, 2, right? So we're starting right here. And then what we have is we need to calculate the new value of y, right? Because it's going to move based on that tangent line slope. Okay. And that's going to be these values we're recalculating. We know that the x values are going to be every 0.5, or there are 4 of them, right? 4 new steps. The question is, how do we get that number right there? Thanks, Jansen. Okay, it involves using this bugger right here.
Well, if you want to see how much y changes per
Exactly. Yeah, so what does dy equal? xy dx. Right, so that's what we put here. And you just plug everything in that you know. What's x? Y. And what's the change in the x value? 0.5, right? So that equals 0 in this case. So we're still at 2. So you've just calculated how much the y changes, right? You okay with that? I'm not going too fast.
I'm just trying to do it again. So I can
Okay. All right, so what's our new x value here? 0.5. Our y value is 2, right? And our 0.5 is still our step every time. Okay, so what does that give us? 0.5. So this would be 2 plus 0.5. Right, so it's this value plus that value. Okay. Whereas this one here was 2 and 0. Yeah, exactly. So 2 plus 0 is 2. 2 plus 0.5 is 2.5. All right, so what's the next row going to be? And what's x? 1. Y is 2.5, and the change is still 0.5. So 1.25. Yeah. So what's my new value here? Yep. And then you do it one more time, you're going to get your approximation for 2. Right, so, ooh, running out of colors here. Let's go with orange. So 1.5 times 3.75 times 0.5. Do that one in your head.
Approximately 6.56.
That's what this is going to be. What is this? Just for posterity's sake. So you see how the progression goes? So your approximation for y at 2 is 6.562. Okay. So x, y, differential, change in y. That's Euler's method. See how it ramps up? The slope changes every time. What you're doing is calculating the change here with the slope and all that stuff. So. Now the question you can be asked is, write words in English with that big of a space. Y at 2. But 6.5625 above or below y at 2. Same question as before. Same deal. Is y concave up or concave down? That's the question. Right. How would we determine that? Second derivative. Anybody? Y plus x dx. So y plus x times xy. If I plug these numbers in, is it positive or negative? It's positive, right? So we're concave up. So the approximation is below y at 2, correct? You can, if you wish, get into error analysis and figure out actually how far that is away, those two are away from each other. That's part of what your book does. We're not going to worry about it. Okay, so you can figure out how far away they are, what percentage amount, and how accurate it is, and all this other stuff. We'll get into a little bit of that with series, but we're not going to worry about it here. All right, that's Euler's Euler's method. Questions? No? I think I have 3 problems for you from the book. Yeah, 14, 15, and 17 from 9.3.
Is that nothing?
Boom.